This is the Building Automation Monthly Podcast with Phil Zito, episode 112. Hey folks, Phil Zito here. Welcome to episode 112 of the Building Automation Monthly Podcast. And in this episode, we'll be discussing how to program a building automation system. So we're going to be covering what programming is. We're going to talk about programming software, different methods and processes, and things like that. It's going to be a lot of fun, and you're going to learn a lot about programming in the process. I apologize for my voice. I'm just getting over a nasty case of bronchitis. So I'm still getting my voice back. I actually ended up missing last week's episode, which was a first for me. But with that being said, we're back and we're going to have a lot of fun. So I've got a core question before we really start to dive into programming. And this is something I always want you to be asking yourself whenever you're going to write a program. I want you to think about this question, and it's really important that you do. And I think by the time we get done discussing it, you should see why it's so important. And that is, why am I doing this? So for example, let's say that you need to connect points between multiple different controllers. Why are you using network variables? Or why are you using a supervisory variable? Why are you making the decision you're making? Think about why. Think about the surrounding implications of that why. So, for example, if you are riding on a pretty steady IP-based network that really doesn't have any downtime, peer-to-peer sharing may be great. On the flip side, if you're doing something where the supervisory device is always up, but maybe you've got a bunch of remote field controllers that, who knows, maybe they're using microwave to communicate between site to site, or some form of point-to-point communication. I've seen that in the past, and communication's unreliable. In that case, you may want to use supervisory devices to send data, to send network variables. So why am I doing this? Or for example, why are you using a PID loop? I see so many folks go and use PID loops and they just drive themselves batty trying to tune this thing that they don't need. In a lot of cases, using proportional control would be just fine. And don't worry if you're like, I don't know what proportional or integral or derivative or PID even means. In the next episode, we're going to go through what each of these kind of logic blocks are. It'll probably be a longer episode, but we're going to dive into each one of those. But why? Why are you using these kind of blocks? You really need to think through that. Don't just use blocks because everyone else is using the same logic blocks and everyone's telling you, hey, you need a PID loop to do this. In a lot of cases, you'll find you don't, and you'll make your programming easier, and you'll make the person coming after you who has to troubleshoot it a lot easier for them as well. And then finally, why is the alarm in code or runtime or, any other factor that could be done in a supervisory device? Why are you doing that in code? I see that a lot in a lot of programs where folks will write their alarms in code. They'll go and they'll write their runtime totalization in code. And in some software, you don't have a choice. You have to do it in code. I realize that. But there's a lot of software where you do have a choice and you don't have to do it in code. And in those situations, you got to think, for example, the alarm. That's the most prevalent one. There are certain situations where you do want latching alarms in code, mainly lead lag control or failure to start, those kind of things. However, on the flip side, there's a lot of situations where you don't want alarming in code. For example, going over your runtime hours. That's an alarm that necessarily you may not want in code. It just depends on the sequence. So once again, ask yourself, why am I going about doing things the way I'm doing them? Now, here's something I've learned over the years. It actually is quite easy to learn to code. And I know for some of you listening to me say those words, you're kind of nodding your head in disagreement. You're like, no, it's not easy. I've been trying to learn code, Phil, for several years. It's not something that's easy. I'm just not a tech person. I'm just not cut out to code, etc., etc. I would say listen to what you're telling yourself right there. I mean, you're basically giving yourself an excuse to fail, and you're sitting there and telling yourself, I'm not technical, I'm not a coder, da 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 da, and then your brain is just going to go and execute that reality. So there's part of a mental game in this, which is that you need to get your mentality right first. But beyond that, the thing is that let's think about how we're taught to code these days, okay? You go to a manufacturer training program and you're given a workbook. And this workbook guides you through the process of writing a couple different sequences. But I mean, there's not a lot of context. Oftentimes, you're at the mercy of whoever the slowest person in the class is, and the instructor is trying to focus on 20 plus different people at the same time. And what it becomes is, oh, well, you lay down an AND block and you connect input 1 to input 1, and you connect input 2 to input 2, and then output 1 to this. And you're getting all this instruction, but you're not getting it with context. And that's the key to learning how to code. Why are you using an AND block? Why are you using an XOR block? Why are you using a NOT block, a flip-flop block, a one-shot block? All these different logic blocks, why do you use them? Why is it important that you use them? Why is it important that you don't use them? When do you use them? And what are the effects to your program if you use them? These are all the contextual things that you need to learn and become aware of. And once you do, then you can really go about learning how to write code. And so you need to ask yourself a couple questions to get into that mindset of context. And those questions are, where will the code be being used? That's a very important question to be able to answer. The type of code you write for a commercial office building is going to be completely different than the type of code you write for a containment room. Now, some folks will argue with me and they'll say, well, no, Phil, that's not true. You would go and a VAV box code is a VAV box code, but really is it? So think about it. A VAV box code in a containment room is often going to be driven off the pressure in the room and the pressure outside the room, and you're going to be trying to control positive pressure in the exterior of the room if you're trying to contain things inside, and in the interior of the room if you're trying to contain things from coming inside. Okay, so that is completely different than just doing basic CFM control in a commercial office space where you often have a tolerance of 2 to 5% where you can be off of your calibration, or of your control rather, to that CFM. So where will the code be being used? That would be two completely different programs you'd be writing. Who's going to be reading the code? That's another thing. You need to think about, how's this code going to be used after the fact? Now, I'm firmly an advocate of going and writing your code in a way that makes it easy to read for everyone. However, the reality is that you need to know who's going to be reading your code, because the thing is that you can get away. I honestly hesitate to. That's the hesitation you're hearing in my voice. Is I'm not sure if I want to tell you this, but the reality is, if you need to, you can get away with some sloppy code if the person reading it after you is someone who really understands code. However, if it's someone who really doesn't, or someone who may not, then you really want to take the time to format your code. I'm just going to be real with you. As much as we want to make our code beautiful, we don't always have the time to do that, especially nowadays where it seems like every minute is being watched on the job site. And finally, is the code user dependent or independent? Now, this is a huge one. And I know we haven't got to what programming is yet. We haven't got to logic blocks and all that stuff yet. But I really want you to embrace these kind of mindset and principle-based thinking processes that I'm laying out here. That when you embrace this stuff, it's really going to make a difference in how you write code, as well as how good of a programmer you are. And so this one's huge. Will the code be independent or user dependent? Think about that for a second. What do I mean by that? Have you ever stopped and thought to yourself, should this set point be externally exposed or not? That is user dependent or user independent, okay? When you expose your set points for that program, you're making that program user dependent, meaning that if that user wanted to, they could go change ilim, imax, k factors, prop bands, they could change timers, they could change stage up and stage down interval delays. They could make a lot of changes depending on what you expose. I always lean towards making it user independent. That's always been my go-to in most cases, because my experience has been that even though a lot of folks think they understand BAS, and they do, actually, they do understand that. That's not a fair statement for me to say. They do understand BAS. The problem, however, lies in that without being able to see into that program, which a lot of folks aren't comfortable going into the programming software, they don't understand the context and impact of changing various set points. So, quite honestly, when you think about it, your stage up, stage down timers should probably never change. Your PID loop variables, your ILIMs, your IMAXs, once properly tuned, should probably never change. So why are you exposing these variables and making them user dependent? So many service calls that I've been on are tied to user dependency issues. I've seen that time and time again. And quite honestly, the easiest way to solve user dependency issues, not create them in the first place. Okay, so now let's dive into the original plan for this episode. What is programming? Well, when you think about it, what's going on, so I've talked about this in some past episodes, right, about the advent of DDC controllers, of direct digital controllers, and why it was so important. So I'm going to give you a very brief recap. Essentially, the majority of the values we read out in the field are analog. So pressure, temperature, voltage, etc., they're analog. They vary between multiple different points. And when I say points, I mean that they vary between 0 to 10, 0 to 4095, etc., etc. But here's the thing. A computer with a processing unit can only accept digital inputs, ones and zeros. So we have a problem. And in order to solve that problem, we invented these controllers called DDC controllers. And what they do is they take analog inputs from inputs like temperature and humidity, etc., and convert them to digital signals. Now, the beauty of that is that allowed a processor to be inside that controller to interpret those signals and then make decisions and drive outputs. Over the years, what happened is that we created field controllers that manufacturers would have programming software, and they would allow you to write line code, and that line code would execute certain functionality based on what the inputs were doing. Over time, folks realized that writing line code was a little prohibitive. You had to have more of a computer science background to understand things like for loops and while loops and if-else decisions and things like that. And in order to be able to do that, what folks decided was, hey, why don't we do something called abstraction? And so abstraction is where you basically take the complexity away by putting a layer on top of it to mask that complexity. So think about it, right? It's kind of like one of those pull-away puzzles where at the first level you look at it, it's very simple. You pull away a layer and then it gets more complex underneath. Well, that is what graphical programming, which is what most programming software uses these days. Not all, but most. That is what graphical programming is. It's a layer of abstraction. It allows you, rather than writing loops and if-else, so for one of the easiest examples, instead of if-else, you use a switch. A switch is a graphical representation of writing the code if else. And if else code is where you say, if this condition's true, we do this. Else, if this condition's not true, we do this. And that's a basic switch, right? You have a binary input coming to the switch, an on-off input coming to that switch saying, hey, if this input is on, state 1 passes through. If this input is off, state 2 passes through, or vice versa, depending on how your switches are controlled. But what's going on here is that you've got this layer of abstraction. So this programming software was created, and this programming software allows you to go and add inputs, outputs, and variables. So let's take a second and talk through those, okay? Because a lot of folks, when they first go to manufacturer training or they first start to work with programming software, they're not fully versed on what inputs and outputs are. So a lot of folks will sit there and say, oh yeah, I know inputs and outputs, but do you really know inputs and outputs? So there's two main kinds of inputs and outputs, and those are physical and network. Let's dive into physical first. So physical inputs are things like digital inputs. Those are on-off signals. Voltage inputs, those are things where you've got a voltage signal and that voltage signal gets interpreted to a value. A common one would be 0 to 10 volts being interpreted in your controller to 0 to 100 relative humidity. That would be a common one. And then another common one is 4 to 20 milliamps. And then there's kind of ones like pulse width modulation, things like that, where they're not as common, but they're inputs nonetheless. Now, of all these physical inputs, they have representation inside the software. And this is really important, so pay attention here. This is where a lot of folks get hung up. When you go into the software, and this is the reason I use the programming software I do in my programming course that I teach, because it doesn't take this away, and I want folks to learn this. But what's going on is that when you bring in a digital input, you are bringing in a Boolean input, a on-off, a 1-0, a two-state input. It can only be two states. It can only be on or off. So that's Boolean, okay? It's really important that you understand that, because if you try to connect a Boolean point to a float, which a float is a point that allows you to have decimal precision, okay? So what does decimal precision mean? Well, if you think of the value 76.6, that has decimal precision. I have an extra level of precision, of preciseness, by adding that 0.6. However, that requires more memory in the controller, so that is a different type. Okay? And finally, and there's floats, doubles, things like that, but mainly you'll hear float. And finally, we have integers. Integers, which I can never pronounce that word to save my life, are whole numbers. They're 1, 10, 11, 15, 20, etc. Whole numbers are also very important, but you need to be aware of their limitations. So for example, if you have a comparator which compares two numerics, two numbers, and then makes a decision based on those numbers, if you pull in a float, which in most cases you will pull into numerics, and you pull in a integer, some blocks won't even work like that. Some blocks won't accept that because of the data type mismatch. Other blocks will accept it, but you'll run into problems because you'll get scenarios where that decimal precision of that float will go and potentially cause issues. Now, that's all well and good, right? But what does that have to do with programming? Well, quite frankly, it has everything to do with programming. Understanding your data types is supremely important. Now, when you're doing most programming software in the market these days, you're not going to have to add a block that converts something to Boolean or to float or to int. What you will do, though, is most of the logic out there these days will say, oh, you've got a Boolean point, you're trying to pull it into a comparator that's looking for a float. I'm just going to tell you you can't add that point. And you can get really frustrated really fast if you don't understand that there's different data types. This is a hard concept for a lot of folks to understand because a lot of folks don't have a data background. They don't have a programming background. And so for them to go through and understand this, it's not necessarily natural. All right, outputs. So outputs are pretty much the same. We have a couple different output types. We have, our digital outputs. These can be straight 24 volts that command a relay, or these can be dry contacts that allow 24 volts to source through them. And then these contacts open and close. So they wouldn't be dry if you're sourcing voltage, just so you know. So I don't want you to be confused when you hear dry and then they're actually wet because you're sourcing voltage through them. So those would just be contact closures. And then you have 0 to 10 volts and you have 4 to 20 milliamps. Those are your most common output types. Now, when you're using outputs, you quite often are using two different types of outputs. You have a Boolean output, and then you have a configurable output. And inside the programming software, you'll configure whether it's 0 to 10, or you'll configure whether it's 4 to 20, etc., etc. So those are the first two pieces of programming, right? So what is programming? It is a way for us to write code that our processor can interpret and then take data from inputs, process it, and drive outputs. But there's two more really important things that we need. The next is called variables. And in the world of variables, there's really two kinds. You could argue three kinds, but there's two kinds for what we're focused on right now. And those are constants and not constants, or variables. And what these allow you to do is these allow you to go and provide set points. These allow you to provide tuning factors. These allow you to provide stage up, stage down delays. Now, earlier on, I talked about user-dependent versus independent code. And this is where we're going to circle back to this, right? So if I wanted to make my code largely independent of the user, what kind of block do you think I would use? What do you think I would use a lot of? If you said constants, you'd be absolutely right. Constants variables are what we want to use when we don't want to expose those points for control outside of the program. Now, a common misinterpretation is that with constants, you can't discover these outside the program. You can quite often discover constants outside of the program. You just can't do anything to them. They're not writable. Whereas variables that are non-constant, those are writable variables. You want to use those sparingly. You want to focus on those for only the most important set points, because you will make your user's life a living hell if you have 40 different variables all mapped in. And I know this from experience because I used to do this. I thought I was doing folks a favor by giving them all these different variables that they could control, only to realize that it just added confusion and complexity, and it just made it that much harder for the user to actually use their programs. So you want to be aware of that as well. And then finally, the fourth piece of any programming software, some would argue the most important piece, is actual logic. I mean, right? You write inputs, outputs, you get your variables, but without AND blocks and OR blocks and switches and flip-flops and muxes and PIDs and sequencers, what are your programs going to do? They're going to do absolutely nothing. And so that is why it's so important to understand the logic blocks, which, like I said, we're going to cover in the next lesson. And these two lessons are probably going to go a little bit long because there's just so much I've got to cover in these. Now, I mentioned a little bit about programming software and methods. There's really only two ways to write programs, and that is line code and block logic. Now, line code, it can be very, very intimidating because a lot of manufacturers who still do line code, which I don't know why they still do line code, you're not doing your programmers any favors. You're not doing your owners and customers any favors. Just quit being lazy and actually change and use graphical programming software. Don't tell me it's more powerful, because I could do anything with my graphical programming that you could do with yours with the right logic blocks. And I challenge anyone to prove me otherwise. Subroutines, complex nested for loops, nested while loops, etc. Yeah. Now, okay, I will be fair. There's one thing. If you're looking to do true coding, like data adapter patterns and parsing arrays and stuff like that, okay, in that case, yeah, you need line code for that. But, that's like uber geekdom stuff. For 99% of the programs out there, block logic, man, oh my gosh, please just add block logic to your software tools. It just makes everyone's life so much easier. You could write line code, but it's slower and it's just nasty. Now, don't get me wrong. A lot of you out there write line code. That's what you do, and you love it. And it is good stuff. I'm just saying the learning curve to learning that versus learning visual programming is much higher, because you have to learn actual programming concepts. You don't have to learn an if, you don't have to learn whiles, you don't have to learn fors, you don't have to learn arrays, all that stuff when you're doing block programming. You just don't have to learn it. It's just not there. So those are kind of the two types of programming methods that you'll have. You'll have, like I've mentioned, straight line code, and then you'll have visual logic blocks. And the way that we add logic blocks to line code is through the process called abstraction. Alrighty, moving right along. The programming process. So this is, I know. I say this is super important all the time. I gotta stop doing that, because there's so many things that I think are super important, and I'm afraid if I say this is super important too many times, you're gonna think nothing's important. But this truly is really important, so pay attention to this. All right. I see a lot of folks who come into learning programming, and they come into writing code, and they have no process. They just read the sequence, and whatever shows up on the sequence is just what they write, and if they write it at all. And their code ends up being a jarbled mess that is really hard to read through. Half the time it doesn't work, and it's just chaos. So I'm going to share with you my exact 5-step process that I've used time and time and time again, and this process is yet to fail me. It's an awesome process, and in my opinion, it's one of the best ways to write code. If you learn this process, I think you will agree as well. So, step 1, we want to add our inputs and outputs. Now, in the next episode, I'll be talking about sequence interpretation, about how we actually find our inputs and outputs, how we actually find our logic. Right now, you just need to go with me. And in the next episode, we'll actually go through how we do this. But the first step is to add your inputs and outputs, okay? So you've got a list of your inputs and outputs. We're talking physical inputs and outputs here, folks. And you go and you add them to your program. Now, typically, you'll put the inputs on the left and the outputs on the right. Next up, we have step 2, which is defining variables. Now, we remember what variables are. At least you better remember what variables are. Oh my goodness, I just told you. All right, but seriously, variables, we start to add those as well. Now, this can be done one of two ways. You can put all your variables on the left, or you can actually put them in the program logic itself, meaning, kind of in the middle or wherever you start to use them. Honestly, I have no preference either way. You can go and put them all on the left. That makes it a little busy. You can put them in the middle. That makes it a little busy. It's just whatever's easier for you to read. Now, you don't want to have inputs all over the place. You definitely want to have those on the left, and you want to have your outputs on the right. So then step 3, we write our Boolean logic. Now you may be saying, okay, this word Boolean sounds familiar. It means on off. Yes, you are absolutely right. So what kind of logic do you think would be Boolean logic? Well, if we have to open a damper, if we have to turn on a fan, if we have to enable a pump, anything that's got an open, closed, or on, off, or start, stop position, this is Boolean logic. Now, the reason why you want to write Boolean logic first, and I didn't realize this for the longest time, I used to write my Boolean and my analog logic at the same time. But the reason why you want to write Boolean logic first is quite often your analog logic is dependent on your Boolean logic. Think about that for a second. Well, I guess first off I should tell you what analog logic is. Analog logic is anything like fan speed command, pump speed command, valve command, etc. Stuff where you're going from 0 to 100 or whatever value you're using. So why do you think maybe fan speed would be dependent on fan command? I mean, think about it. If the fan's not on, it doesn't matter what speed the fan is, it's not on. So that's why it's so important to write your Boolean programming before your analog. This is a tiny little nuance, but this little nuance, this little nuance has made such a difference in my ability to write programs. Oh my goodness. Once I figured this out, that, man, you write the Boolean logic first, and then you write the analog. Oh my gosh, because think about it. If you've been writing code for a while, you'll probably totally relate to this, where you're sitting there and you're writing this code, and you started and you wrote the pump speed or whatever just because that's what was first in the sequence. And then you write the pump command, but you miss something. Maybe you missed the enable of the PID loop, or you missed some AND block connection because just the order you've wrote it in. And no matter what you do, you can't seem to get this thing to start. Or the pump VFD starts before the pump, or it's just all sorts of craziness. And then you realize, man, what if I just wrote that Boolean code before the analog code? So that is the long way of explaining why step 3 is so important. And then naturally, as I mentioned, step 4, writing your analog logic. So this is where you're going to go and you're going to write out the logic that controls these analog things. Analog things, once again, being things that are 0 to 100, 0 to 50s, 0 to anything more than 1. So they are not on, off, they are analog, okay? And then finally, step 5, and this is super duper important, and this is writing your safety code last. I used to just follow the sequence. When I was a young little programmer who had a full head of hair, I would sit there and be like, you know what? I'm just going to follow the sequence. Because that's what I should do, right? Follow the sequence, write the code, follow sentence by sentence, write that code. And that's how I wrote code. Because I didn't know about sequence chunking, I didn't know about sequence interpretation, all things you'll learn in the next episode. But because of that, quite often, I would go and write safety code, and this safety code would actually be something that wouldn't work. And think about that for a second. Smoke stops start, low temp cutouts, high pressure, low pressure cutouts. Even though you have physical safeties, you oftentimes will write code for these as well. And I would have code where this stuff wouldn't work. That's not good. That's actually really, really bad. And it was because I would be writing code, I would come along where there would be a fan failure condition. I'd write that fan failure condition, but then, a paragraph later, there'd be another code that would overwrite that fan failure condition. And because I didn't write my failure conditions last, they would get overwritten by the code. This is why it's so important that you have a programming process. A lot of folks who tell me, Phil, I can't write code. I'm not a programmer. I can't figure this out. My programs don't work. They're confusing, etc., etc., etc. When they actually start to embrace this programming process, those challenges, those beliefs start to disappear. Because when you have a process, it is literally as simple as following the process. And like I said, in the next episode, we're going to go through how to chunk out sequences and sequence interpretation. And that's like pouring gasoline on the process because it makes it even more powerful. All right, so what did we go through in this episode? We went through a ton, right? Went through why it's so highly important to understand the context of your programming efforts. We talked about what programming is, inputs and outputs, went through programming software and methods, and the programming process. So as you leave this episode, I really want you to internalize what you've learned today. This was a very tactical, very hands-on episode where you can take a lot of what you've learned in today's episode and immediately apply it. And that is how you're going to learn. That is the best way to learn, is you need to take what you've learned in today's episode, and I want you to go and immediately apply it to your programming efforts. So start writing your programs this way. It'll be uncomfortable at first. I'm not going to lie to you. It will not feel natural. You'll find yourself challenged. You're going against muscle memory. You're going against the way you may have been taught. You're going against how you've done things in the past, which quite honestly, for a lot of programmers, they don't think about what they're doing. They just write the code. Now, you may be saying, Phil, I think I'm a smart person. That's not what I mean. Get off your ego high horse. I'm not insulting you. What I mean by that is that you don't have a process. Yeah, you think you're smart enough to interpret the sequence and create code. I don't disagree with that. But you're not using a process. And that process will make your code so much better. I myself all the time am looking for processes in everything I do, because they make my business more efficient, they make me more effective, and they give me back time, and they make sure that I make less mistakes. And gosh knows, I can always deal with making less mistakes, because if I have one weakness, I would say that my ability for attention to detail is probably not the strongest out there in the world. But hey, we all have our strengths and weaknesses. So with that being said, thanks so much for listening. Once again, I apologize about my voice. Hopefully next week it'll be fully back. This bronchitis crap, holy moly. Man, I was smacked down. I was like coughing for 2.5 hours, just feeling horrible. But hey, I'm back. I'm talking. Drugs are amazing when used properly, kids. But, oh God, I'm going to start coughing if I laugh. Anyways. So, you want to learn more about programming. You found this episode to be super fascinating, but you really want to get hands-on. You want to learn how to program in 2 weeks, be able to go and actually start writing programs in the field, future-proof your career, and make sure that you really, truly have mastered the skill of programming. Well, I got good news. My latest course, BAS Programming Fundamentals, is out, and it is absolutely freaking awesome. This course takes you cradle to grave through the programming process. We look at every single logic block in detail. We dive into the programming process. We go through a series of design patterns, and these design patterns are what are going to make you an amazing programmer. You see, a lot of folks try to write code from scratch, or they try to copy someone else's code, but they really don't know what's going on. With design patterns, you're able to understand the underlying logic blocks and the way that the code should be written for specific sequences, for specific actions. You have a fan that you need to start and stop and make sure it has a manual reset. You have a design pattern for that. You have CO2 control of an economizer. You have a design pattern for that. You have lead lag control. There's a design pattern for that. You shouldn't have to go and reinvent the wheel. And with this programming process, you will learn how to build these essentially Lego blocks of programming and piece them together to build your programs from scratch. And build we will. There is a ton of programming in this course. I've worked with the manufacturer to get access to their virtual controller as well as to their programming software so that you can follow along hands-on and be writing code from day one in the course. And then finally, we close out the course by creating 3 complex programs: a VAV reheat, a rooftop unit with economizer and CO2 control, and finally an air-cooled chiller with lead lag pump control. So we're going to cover all the basis of programming, and you will come out of this course as a powerful programmer. This course will change the trajectory of your career, and I encourage you, so encourage you to enroll in this program because it will change your career for the better. So find out more about that at buildingautomationmonthly.com/112. Once again, everything that I discuss, like always, will be available at buildingautomationmonthly.com/112. Thank you so much for being here, for listening to this episode. I'm so excited to be back behind the mic and talking to you again. And I can't wait to record episode 113 with you. It's going to be awesome. And we're going to really bring some of these programming concepts home. Thanks a ton for being here. And I'll talk to you all again next week. Take care.